So in this video, we're going to talk about a half-life. And a half-life has to do with radioactive material. Radioactive material is going to decay. And a half-life is how long it takes to decay to half the amount you started with. So if you started with 100 grams, then how long does it take for it to get to 50 grams? However much time that is, that's the half-life. Now they have a table in the book, I didn't put it in the video, that shows you different half-lives. Some materials have like a 6-hour half-life. Some have like a 6,000-year half-life. So some are in hours, some are in years. It just depends on the material. Okay? All right, so that's what we're going to work with in our problem here. They've also given us a formula, and it's similar to like a compound interest formula. You're saying the amount that you have after so much time. It's based on the initial amount. So A naught, I'll write it over here. A naught is the initial amount. It's what you started with. And then little t is time. Now that time could be in hours, it could be in years, it could be in days. And then the uppercase T, that is the half-life. Oops, half-life. Okay? And this is how much you have left after so much time. So A of T is the amount after T. And the T could be in hours or days or years. Okay, so we're going to use that handy formula. There it goes. How long will it take for 10% of a 1,000-gram sample of uranium to decay? Oh, to decay. There's the question mark. Sorry. How long will it take for 10% of a 1,000-gram sample of uranium to decay? Uranium 235, by the way, uranium-235. And that's just an isotope of uranium. Isotope. Okay, so part of the name of the material we have. So uranium-235 has a half-life of that many years. So 703 billion years and 800,000. I'm sorry, million. 703,800,000 years. Okay, well, still a long time. Okay, that's how long for it takes to decay to half the amount. Okay, so let's see. We want to know how long it's going to take for 10% of this to decay. All right. Okay, so if 10% is going to decay, then we're going to have 90% of what's left, right? So what's 90% of 1,000? 900? Okay, so we want our A of T to be 900. Yeah, okay, that means 10% would have decayed. So 10% of 1,000 is 100, and so 100 grams is going to decay, and we're going to have 900 left. Okay, so I hope that part makes sense to you. We know the half-life. It's that huge number, 703,800,000. 703,800,000. Okay, that's the half-life. And we're trying to figure out time, right? How long will it take? We're trying to figure out the little t. We also know how much we're starting with, A sub 0. Okay? All right, so let's put this all into the formula. So let's find the formula. A of T equals A naught. A lot of times we'll say A naught. 1/2 to the power of little t over big T. They show you a little bit in the book where that formula comes from, but we'll just use the formula that they give us. Okay, so we want 900 grams. Yeah, grams. We're starting with 1,000. And then our little t, that's what we're trying to figure out. And then the large t is 703,800,000. We're going to do some calculator work here. Okay, and now we want to solve that equation. So the first thing we're going to do is divide by 1,000. And I'm going to go ahead and make it a decimal. So it's going to be 0.9. That'll be easier for me to write. And I can even make the 1/2 a decimal as 0.5 to the t over that big number. You can't really get around that big number for a little bit here. Okay, now I can take the logarithm of both sides, or I could write it in logarithm notation. I would probably just take the log of both sides. So I'm going to use my natural log. Natural log of 0.9 equals the natural log of 0.5 to that exponent with that big number in it. We really care about that uranium. Okay, now, in the past, when we took natural log of both sides, it seemed like a lot of times we were able to just go with the exponent because it matched. This time it doesn't. This is an E base, and this is not an E. It's 0.5. So we don't get to do that part. But what we can do, we can bring that exponent, that very large exponent, well, it's not very large, but the denominator's got a lot of digits in it, we'll say that. We can bring that down in front times the natural log of 0.5. So what I really want to do is solve for t. I can multiply by that denominator, 703,800,000 times the natural log of 0.9 equals t natural log of 0.5. Now remember, this is just a number, so I can divide on both sides. So I'm going to have that's what's going to equal t, the left-hand side there. Okay, so I have to put all of this in a calculator. That's the exact answer. But t is going to equal, and so I'm going to put in my calculator that big number times the natural log of 0.9, and then I've got to divide it by natural log of 0.5. And I'm going to get a decimal approximation here. So let me grab my calculator and clear it out. 7038, 1, 2, 3, 4, 5, and then natural log. Remember, it opens the parenthesis, 0.9. Make sure you close that parenthesis right there. That's really important. Divided by natural log 0.5. Close that off. And I am getting, oh, a very big number. Yep. Well, let's see. 106. It didn't say to go to the nearest year. I think I'm just going to go to the nearest year, though. 106,979,777. I have a 0.2, but I'm just going to go to the nearest year. Wow, that's a lot of years for that 10% to decay. Okay, so it's decaying very slowly. It's going to take a long time. 106,979,777 years for 10% of uranium-235 to decay. Okay, well, that was a fun problem.